certain tasks can only be done once another task has already been done first. Okay? So, here's a simple example. If I gave you a network activity A, okay, so A takes you, 3 minutes. Okay, so I'm going to do 3 minutes there. Activity A takes 3 minutes, and then I put it over here. This is activity B. So activity A, then activity B follows. Activity B takes, say, 4 minutes, right? At the moment, if I follow this pathway, how long should I account for in order for this entire process to complete? How long? 7 minutes, right? Now, I'm going to write in red just so that it's on the side that you can see here. So currently, 7 minutes is your total time, or the minimum time, or the longest time that you need. But if I add another line, or another network or activity, and I said that you can actually just do the job by hiring one person, and they're a master chef, and they will do it one person to do, so it may cost less, but it does take them 9 minutes to do, right? Now, if I asked you, if they all work in a team, you got person A, person B working to finish their job by this point, so this is the finish time, this is the start time, then in total, how much time should you account as a business person hiring A, B, and C? How much time do you need for them to all complete their task? How much time would you need in order to ensure that they all will complete their task? 9 minutes. Because you can't say 7 anymore, because at 7 minutes, this guy's still finishing off his work. Part C, activity C, is still working, and they take 9 minutes to complete. So you can't say that you only need 7 minutes anymore. Your minimum time required is 9 minutes. So this is where the language in the exercise may sound a bit confusing. They'll ask you, what is the minimum time required for the entire process to complete? What's interesting is you'll find it the longest pathway. See how it's different to Dijkstra's algorithm? You were looking for the shortest pathway. Here, we're looking for the longest pathway. So we looked at it, 3 plus the 4 gives you 7. True, they will finish it the quickest, but we're not interested in that. We're trying to account for the time so that we know what's the minimum time required for a process to finish. So these things could be like cooking. What's the minimum time required for you to finish your cooking process? Cut up the ingredients, cook your ingredients, present your meal on a dish. How long does it take minimum? Right? So when they say minimum time taken, it actually ends up being the maximum time that a person or activity should take. Okay, that's the sort of contradiction that gets a bit tricky. So now that we understand, okay, so we're looking for the longest path. Using what we understood about Dijkstra's algorithm, this is what I'm going to teach you. We don't need to do this idea of boxing. It's nice to have the boxing, so I wanted you to learn the boxes first from the first session. But now that you've got a general idea of what the boxes mean, you don't have to do it for all of them to then answer the questions. You can avoid doing all that and then use a bit of logic to figure it out. So I'll show you some examples, but for those who haven't looked at exercise 15D, EST, LST. EST refers to the earliest time that a particular activity can start. LST refers to the latest time that a particular activity can start. So say that this is the starting point, right? Then the starting point for A, so activity A, this is the starting for activity A, this is the ending time for activity A, but also the starting time for activity B. Activity A obviously starts, earliest time is they can start at right from the get-go, right? But it doesn't mean that they have to. But let's have a look here. If they started at the earliest time, which is 0, by the time they get to finish A, what's the earliest time that activity B can start? 3. Because it takes 3 minutes for activity A to complete. So if they started from the get-go, then B can start the earliest at 3. And then if that's true, then if activity B started at 3, how long does it take for you to finish? What's the earliest time that it can finish? 7. And what you've done here is you've done 3 plus the 4. This is called forward scanning. which is, if you go through the videos that I go through, that's what they're teaching you. Now, let's go backwards scanning. Okay, let's go backwards. If I went backwards, so starting from here, clearly there's a 7 minutes. That's the aim. Okay, you want to finish by 7 minutes. That's the, I'm not accounting for the 9 at the moment. I'm just looking at the top row. So at 7 minutes, if I went backwards, this will tell me the latest time that activity B can start. So I said the earliest time can be 3, but it doesn't have to be. Because remember, they just need to finish in 7 minutes. They need to make sure they finish by 7, right? So from 7, if I go backwards, I'm minusing the 4 minutes that it takes for activity B. 7 minus 4 happens to give me 3. 3. So this happens to tell me that actually, well, no. If you want to finish by 7, that means that 3 and 3 are the very critical in the sense that they have to start at 3 and they have the latest time that they can start is also 3. So there is no give way for it. And then when you go backwards here, that means that if this is the latest time B can start, then the latest time that A can start has to also be then 0. Because if it's not 0, it won't work. Now what you see here in this activity, this is called a critical path because it means there is no give way between the earliest time and the latest time. If I said the earliest time you can start is now, or the latest time you can start is now, well, you can only start now. You don't have any other freedom. So that is called a critical path because any one of them who screw up take longer, then it delays the entire time. Okay, so the critical path is good for problem solving later on in crashing. So you're going to look for critical paths. But here's the interesting part. This only works and it's only critical because we said it was 7 minutes. But we already know it's not 7. If I include activity C now, okay, let's have a look. What's the latest time that F can finish? If you think about it, from here, I started off at 0. If I started from the get-go, activity C takes 9 minutes to complete. Okay, so activity C takes 9 minutes to complete, and what you can see now is that it will not mean the finish time, the earliest finish time is not 7 anymore, because I can't finish at 7. The earliest time now has to be 9. Now this is where you start to see the giveaway. So 9, and the reason why we choose 9, this is kind of like Dijkstra's algorithm. Instead of finding the shortest path, I'm now looking for the longest path. So what I did before was I only did 3 and then 4, but I didn't account for C. Now that I account for C, that changes what the earliest time this finish point can be, and it has to be 9. What that changes is that if I went from 9 back to here, then obviously the latest time is 9 that it can finish. But what's interesting here is that if we all do this box again now, let's do all these boxes again, you'll find that it changes your longest starting time or your latest starting time. So let's have a look. If you know that the latest starting time is 9, okay, that's the time that's required for this activity to finish. Then going backwards now, going all the way here, what's the latest time that activity B can start if it only takes 4 minutes to complete activity B? And I know the deadline is by 9, I better be done. What's the latest time this can start? Logically. So I have to finish by 9. It only takes 4 minutes to complete my task. When can I start? 5. Logically, have a think about it. So 5, you think about, I can start at 3. There's nothing wrong with starting at 3. So 3 plus 4 gives me 7. That's okay, I just finish early. Or I can wait until 5, and if I do my work at 5, I still finish at 9. So I've got a float time here. I got 3 to 5 is what we call a float time. Then there's a bit of room to wiggle. Okay, it means that I don't have to start. But why did this float time exist? It's because of this new critical path. This person's the only person, 9 and 9 and 0 and 0. This person is what we call the critical path now. It changes the fact that these two don't become important anymore because they have giveaways. This guy doesn't. That's because I'm now counting a third pathway. That's where you want to be training. So I'm going to teach you how to find this critical pathway without having to go through those boxes, because that's what your textbook's teaching you. They're teaching you to do earlier start time, earlier start time, earlier start time, pick the largest value. Once you got them, then you can fill out all of these going backwards. 5 take away 3 gives me 2. So that tells me activity A doesn't have to start from the get-go. They can start at 2, and they'll finish at 5, and then activity B can then start and still finish at 9. Doesn't matter. The only person that did matter was C. C had to start from the get-go and finish exactly at 9. C never had a float time, whereas activity A and activity B do. Activity A has 2 minutes float time, and same thing, that gives 2 minutes for activity B. That's how you would solve the problem. So you then have to find each of every activity has a box. Now you can imagine if looking at your VCA questions, you don't want to be doing, where is it again? Oh, it disappeared. Or maybe it's taking time to load. If you have a look at your VCA questions here, you don't want to be doing those boxes for every single edge. It takes a lot of effort to calculate EST, LST, EST, LST, float time. Each one will take too long. So I'm going to teach you a way to go through these questions without having to do what we just did. Because what I just gave you was a very simple network. It was a 3 process, 3 edges, 3 activities. That was all you had to worry about. But this one, for example, has dummies, and it also has many other activities to worry about. Okay? So, how do we answer these questions and find the critical part? I'm going to show you here. Actually, I'll do